Hello and welcome to our lesson on purification of copper. So far in this topic we've looked at metals that are less reactive than carbon, and we can use carbon to separate them from their ore using displacement reactions. Today we're going to look at what happens when we have elements or metals that are above carbon in the reactivity series. So these metals are highly reactive and they need even more energy and even more help to be separated, and therefore are going to cost more money. So if we look at a standard reactivity series, you might get one that looks slightly different in an exam, but the ideas are still the same and all the important metals will still be present. So don't panic if you see something slightly different. What you do need to know is this line here. Anything below this line is less reactive than carbon, and therefore we can use carbon and a displacement reaction to separate this metal or any of these metals from their ores. Above this line, we can't use carbon, so we're going to need to use electrolysis. Okay, so what do we need to know? So these here, towards the top of the reactivity series, anything above carbon, this applies to, can be extracted from molten compounds. So molten compounds are melted compounds using electrolysis. So you can see why there's a lot of energy going into here, because we've got to melt these compounds, possibly dissolve them if we're really lucky, usually melting them, and then we've got to use electrolysis, which also takes a lot of electrical energy. So this is going to get expensive very quickly. There we go, it uses a large amount of energy. Whenever you're using a lot of energy, that's going to cost you a lot of money. And that is why metals, these metals in particular, tend to be more expensive, because they take so much more energy to extract. Electrolysis, we've done electrolysis in detail in Unit 3, I think. So you need to be aware of that. You need to go back and look at that if you're not confident in that already. But today, this lesson, I want to look at electrolysis being used to purify metals. So that's very different to extraction. Okay, so just be aware of that. This is a slightly different way of doing things. So here you have smelted copper on the left here. So this is copper that has been extracted using displacement reaction. So copper oxide plus carbon making the copper. And you can see here it's still pretty raw, it's still pretty lumpy, it's not very pure. Okay, so this smelted copper is not going to be particularly useful for making the copper pipes you can see there, or copper wiring. And of course, the more pure something is, the better it is going to be at conducting electricity. So we're looking really at electrolysis being used here to produce pure copper from crude copper metal. So how does this work? Well, we use electrolysis to move the copper from an impure lump, that's smelted copper, to a piece of pure copper. So we're looking at through a solution. So obviously we need electrolysis, we need liquid, we need those ions to be able to move from one side to the other, or move to an anode or a cathode. So we're going to need a solution. So the crude copper is moved into pure copper, and then you are separating your impurities. So here's the very basics. We'll go into this in a little bit more detail in a second, but a very basic level here. I have 2 electrodes set up. This is going to be my negative electrode, which is my cathode, because I want the copper, which is positively charged, to be attracted to it. So that's going to be my negative electrode, the cathode, and then here my positive electrode is my anode. So if I turn on the electricity, what's going to happen? Well, hopefully you will remember that opposites attract. So the copper ions are attracted to the cathode. The impurities are not, because they're not charged. And so the impurities just drop out down to the bottom of the liquid, and you can separate them at a later date. So you can see why that would happen. Let's look at that in a little bit more detail though. So there's going to be quite a lot of clicking here. It's quite an in-depth PowerPoint, but just stay with me. Hopefully this will make a lot more sense once we go through it. Okay, so first of all, we need a solution. We need a liquid of copper ions, okay? We talked specifically about using copper. You can use this to purify other metals, but for the syllabus, you really only need to know about copper. Okay, so we're going to use copper sulfate. That's our liquid, that lovely blue liquid, because we're separating, or sorry, we're purifying copper. Okay, so here's our blue liquid. Okay, and next then we're going to need our piece of impure copper. Here we go, and we are going to make this the positive electrode here. So this is, we're going to attach it to our wires here, and that is our positive anode. Next then, we are going to add a thin layer of pure copper, and we are going to make this our cathode, our negative electrode. Okay, there we go. Right, so this is the setup then. Okay, now hopefully you're already starting to think, well, because I've shown that first slide, I know what's going to happen here, but it's the language you can use that's going to kind of separate you from the crowd if you're careful. So what else can we say? So obviously the cathode, the negative electrode, has those negative electrons as well. So we know that as ions move across, they then become atoms at the electrodes. So where are we? Here we go. So it's got some negative electrons. Okay. So then positive copper ions in the solution move to the negative electrode. So don't forget, we've also got copper ions in the liquid itself, in the electrolyte. So they're going to move across to the cathode, and they're going to become copper atoms there, and that's your half equation for higher. If your foundation right now, there's a lot of detail here. You don't need to worry about ions becoming atoms at the electrodes, but higher you do. And again, if I'm going through this too quickly, do look at those electrolysis videos from Unit 3. So that's the ions from the liquid itself, from the electrolyte. Okay, now here are you can see here we've got the copper atoms inside in the impure copper, and they become ions, which means that they are now able to move. Okay, so here we go, they are now moving across to the negative electrode. Now you'll notice the impurities then are kind of working loose because there's less copper. They're going to drop to the bottom of the solution. Okay, and eventually what you're getting is a situation where more and more copper atoms become copper ions, go to the cathode and become copper atoms again. And you'll notice what's happening to the anode. It's getting smaller and smaller as more and more copper moves across. So you might be asked about what happens to the mass of the anode. Well, it decreases because the copper has moved to the cathode. And what happens to the mass of the cathode? Well, it becomes greater as more and more copper is added. And you can see there the impurities dropping out into the solution itself. And there we go, we end up with pure copper. And that's a really good thing, like I say, because the purer the copper, the better it's going to be at conducting electricity for wires and things like that. Okay, so this question is suitable for everyone. I'd like you to pause the video and have a go for yourself, please. Okay, so if we book this question, command word is describe, and it says you may wish to put some labels. I'm going to put some labels on the diagram to help your answer. Okay, so what am I describing? How impure copper can be purified by electrolysis. And if I'm using that diagram, well, first of all, I've noticed this diagram actually has got the anode and the cathode. No, they are the same way around. Sorry, forgive me. I thought they were the opposite way around. It wouldn't matter that they were the opposite way around. I would just need to be careful that I was labeling them the correct way. So positive anode and negative cathode. So I could start there. What else would I label? Well, which one's my impure? Which one's my pure? Well, this is going to be my impure copper, isn't it? The anode, and this is going to be my pure copper, the cathode. And I'm going to talk about my liquid, my electrolyte. That's going to be copper sulfate because it's copper that we are purifying here. So it's copper. So it will be copper sulfate. Okay, so what am I going to say? What am I going to get? 3 marks here. What would we get those marks for? So here's from the exam board. If you'd have said the anode was the impure copper, you would have got a mark. Cathode is the pure copper, would have got another mark. Electrolyte is copper sulfate solution. So actually, simply by labeling that diagram up with impure, pure, and copper sulfate, I'd have actually picked up the 3 marks there. There were other marks available if you'd said that the cathode gains mass, or the pure copper is deposited on the cathode. So if you talked about that movement, or the anode losing mass as the copper moves across. So lots you could have said there, but a relatively easy 3 marks if you had remembered the basics. What I would recommend is you always write as much as possible, as much as you can remember on that topic, just making sure that you're answering the question. Okay, so this question is for higher only. If you'd like to pause the video and have a go. Okay, so again, I'm going to book this question. It says write a balanced half equation. So half equation, is it atom into ion or is it ion into atom? So I'm going to look, it says copper ions, Cu2 plus, gain electrons. It's making it very easy for me. And copper atoms are formed. So I'm going ions into atoms via gaining electrons. So I'm going to write something like this. Okay, and notice there's 2 marks there, 1 for the formula and 1 for getting the right numbers. So noticing it's 2 electrons you're gaining there. Okay, so foundation guys, you don't need to know this little bit, but there are some questions at the end of this lesson if you want to fast forward. But this little bit is for higher only. Higher guys, you need to know that copper is running out, and we need to find more and more scientific ways of extracting even the smallest amounts of copper from rock that we wouldn't have bothered with before, either really low grade or rocks we know that contains copper but we've never bothered with. It wasn't financially worth extracting. So there's a couple of things. Bioleaching is using bacteria. Phytomining is using plants, and we can use scrap iron as well. So let's have a look at each of these in turn. So I've used the dual coding to help you see if you can remember, but the basics is this. So some types of bacteria, not all bacteria, but basically they can break down the rock ore by extracting the metal ions as they carry out their normal biological processes. So during the normal biological process, bacteria will absorb these metal ions from the rocks and they produce an acidic solution. So that's the second part of the dual coding. And this acidic solution is called a leachate. Okay, and this leachate, this acidic solution, contains a high concentration of the metal ions. So the bacteria have concentrated in this case, the copper ions to make it easy to extract. Once we have that leachate, we can react it with sulfuric acid to make copper sulfate, and then we use electrolysis to separate the copper from the copper sulfate. So the advantages of bioleaching is that it doesn't require any high temperatures. You can just let the bacteria go to town on the rocks. However, it does make this acidic solution, which is quite a toxic substance. So that is a negative. Okay, so phytomining then, you are literally growing plants on the low-grade ores. They absorb mineral ions, those metal ions, through their roots, and they concentrate them within the plant itself. You then pull up the plants, you burn them, and then the ash that's left over has this high concentration of the metal ions. You react that with sulfuric acid to make copper sulfate, and then you use electrolysis to separate the copper from the copper sulfate. Advantage, of course, is that we're getting more copper, but it is a very slow process. So finally then, scrap iron can be used rather than electrolysis to separate the copper from the copper sulfate, just a displacement reaction, which is going to use a lot less energy than electrolysis. And the scrap iron is then easier to extract again using carbon. Okay, so foundation and higher, pause the video and have a go. Okay, so the first question is a classic example of several answers being correct. If you're not careful, you've got to make sure it applies to the question. And so the answer is C. Second question, if you were foundation, you would say iron gains oxygen. If you were higher, you would need to talk about losing electrons. And the final one then is A. Okay guys, that's it for this lesson. I'll see you later.